Good afternoon, everybody. Let's get started. For announcements, Lab 4 is in progress, and you'll start Lab 5 this week, so that will be this Friday. You finished up, or you should have finished up Exam 1 by now. I'm still confirming I've received all the exams and have one makeup exam waiting to collect, so I'll get those solutions posted as soon as I can, and then we can talk about that exam. All right. So last time, we finished up talking about power sources, and we talked about a solar panel example. And today we're going to start talking about power control topics. So when I say controlling power or power control, I'm talking about delivering power to a load, delivering power to a device, either turning the power on and off, or controlling the amount of energy or power delivered to the device using pulse width modulation. And so how do you do that? And so we're going to talk about various ways to do that. Some I'm sure you're familiar with. One of those ways is just a manually actuated switch, right? So you change the position of a lever or a button to connect or disconnect contacts within that switch. And there are various configurations of switches. So you have toggle switches, rotary switches, etc. We'll talk a little bit about those and how to describe those switches that maybe you want for to control a load in a certain way. So those are manually actuated devices. And then there are electrically actuated devices. One you've probably heard of is a relay, right? So this is the schematic symbol for a relay. Here are a couple example relays here. And so for a relay, a current through a coil generates a magnetic field, and then it pushes or pulls electrical contacts together or pushes them apart. Okay, so relays are considered electrically actuated. They're very mechanical. Transistors are another way to electrically control power delivered to a device. So one way that we've talked about, if you took my class or any other intro to circuits and electronics class, is the bipolar junction transistor. So these are a few examples of bipolar junction transistors, BJTs. Here's a common package that you would use with breadboards. Here is a surface mount BJT. Here's a larger, higher power BJT here. This is the schematic symbol. And these are current controlled devices. So you typically use IB to control IC in a certain configuration. So that's what we did in class, if you took my last class. So IB is the base current, and you'd control collector current with the base current. All right, so that lets you use just a little bit of current to control a whole lot of current, and that's useful when you have a low power device like a microcontroller. And that microcontroller can output a few milliamps from its digital port, and you could use that amount, that few milliamps, to control hundreds of milliamps, potentially. Okay, the other type of transistor that you're using in lab is the field effect transistor. You're using a MOSFET, a metal oxide semiconductor field effect transistor. Here is the schematic symbol of a MOSFET. MOSFETs are 3-terminal devices. You'll see the drain, the gate, and the source. We're often concerned with controlling ID, the drain current, using the gate to source voltage. But these are voltage controlled devices. Okay, so the BJTs, those are current controlled devices. One current controls another current. In this case, you're using a voltage to control a current. So FET switching circuits typically use the gate to source voltage, VGS, to control the drain current. Okay, and so these are examples of ways to control power delivered to a device, either mechanically actuated or electrically actuated. And there are other electrically actuated switching devices. There are solid state relays, there are opto isolator relays, thyristors, SCRs, etc. So we're going to concentrate on these common ones here that I've listed, and in lab you're using the MOSFET. So we'll talk about that in a little more detail. But let's go back to the top of this slide and talk about switches, just because there's some vocabulary there that's probably useful. So some common switch types. So you've probably seen a toggle switch and a slide switch. So those, to turn devices on and off, they're mounted on the package. There are other types of switches like a micro switch or a limit switch. So these are often associated with either a cam or some kind of mechanical device where when an arm or a lobe hits the switch, something happens. Okay, so here's a micro switch with an arm on it. When you press that down, that actuates the switch. Here's a micro switch that has just a little tab sticking out of it that activates the switch. Here's a rotary switch. Right, those are common for on a front panel, selecting many different options on a device. Here's a dip switch, a dual inline package switch. That's what dip stands for. And so these dip switches are actually multiple switches in one of these packages that fit into what essentially is the socket or the place on a circuit board for an integrated circuit of this type of dip package. Okay, so those are switches. So you'll see dip switches in devices that have some kind of configuration. Like if you open up the battery compartment of something like a garage door opener or different devices, you might see these dip switches, and they control configurations typically. So those are common types of switches. You might have latched versus momentary switches. So a light switch, like on your wall, that's a latched switch. You move it up, it stays up. You move it down, it stays down, open or closed, right? So that's a latch switch. A momentary switch, you can press it to activate the switch, and then you release, and that was only a momentary activation. The switch deactivates it once you release. So if you press this lever down, it does not stay down. It snaps back up. It springs back up. Okay. And so especially for these momentary switches, you'll see designated normally open or normally closed configurations or terminals. So in this case, you have this switch. It's a momentary push button switch, and it has a common and then a normally closed terminal and a normally open terminal. So if you don't touch the switch, then the normally closed terminal is connected to common. Okay, and then when you press on the switch, what was normally open now closes. That contact gets made between the common and normally open. And so someone asks in the chat, would toggle also be considered latched? Yes, so this toggle switch would be considered a latched switch. Now there are switches that look like this that are momentary. So the switch might be in this position here, and then you push back on the switch the way it is in the slide. You push back and it stays there, and you release it and the switch snaps back. So there are toggles, well, there are switches that look like this that are momentary. All right. So this is normally open versus normally closed. Let's see something that is often designated for a switch, and that's pulls and throws. Okay, so you'll see a pull designation. That's the number of connection circuits. I'll show you a diagram. And then number of throws. That's the number of output connections, right? So you can have a single, double, 3, 4 for these designators. For example, here's a single pole, single throw toggle switch. Okay, so it has one connection circuit and one throw. Contrast that to this is single pole, double throw. Okay, so look at these two, right? The single pole double throw is still one pole. It's one connection circuit between a common, but it has two outputs. Two output, I'll say, could be input connections here on the right. Right, so this is single pole double throw because it has two of these connections here. And you can see that this switch on the bottom has 3 terminals corresponding to the 3 terminals in the schematic. The single pole single throw only has 2 terminals. Okay, here's a double pole, single throw switch. So double pole because it has two connection circuits, but each of those connection circuits only has a single throw, right? A single output connection. And then here's a double pole, double throw. So when you change the position of this switch, it moves both of these contacts together, connections together. So that's what that dotted line means. So this is in one position, and when you flip the switch, both of these connections move to the bottom position on the output terminal. So this is double pole, double throw. Okay. And you can get triple pole, quadruple pole. You can get these in different configurations. All right. Here's another switch. Here's a four-way switch. These are typically in homes. And so a four-way switch works like this. So here's the schematic symbol for it. A four-way switch is either in this configuration, right, or in this configuration, right, where there's no connection where the middle of the X is. Okay, so four-way switch either goes straight through for those top and bottom pairs of terminals, or it crisscrosses like this. Okay, so that's a four-way switch. And I'm commonly asked, actually, when I talk about switches, so I put this in here, about this configuration. What happens if you want three or more switches to control a single load, like you have 3 light switches or 4 light switches in your house that connect to one light bulb outside maybe? And so how does that work? That works like this. So you have the power source, your AC power supply, AC power in your house, and you have a light bulb or some other load. And you want to connect, let's say, 3 switches, such that if you switch the state of any of those switches, the light will turn to the opposite state, either off to on or on to off. So this is a way to do that, right? Here's a 3-way switch, which is really just a single pole double throw switch. Here's the 4-way switch I just talked about, and then another 3-way switch. So you can control that light bulb with any of these switches. And in fact, if you need more switches to control that same load, you can put another 4-way switch in here and keep stacking those up. So that's how you can control a load with multiple switches. Okay, so those are common terms for switches. Let's take a look at limit switches, because limit switches can actually be built in some pretty complex logic circuits. So sometimes what you would think would take a microcontroller or logic circuits can actually be implemented with just switches. So limit switches detect the presence of an object or the position of an object or an arm or a lobe on a cam, for example. And you can use these as inputs to digital circuits, right? You could have a switch control the voltage into a microcontroller input. Right? So putting these switches in series with a pull-up resistor or a pull-down resistor is a common way to get a signal into a microcontroller that reflects the switch state. So here's the limit switch. Here it is right here. And in this case, I have a pull-up resistor. So when that switch is open, this Vx is pulled up to 5 volts. The microcontroller sees 5 volts. If something causes that switch to get depressed, then the switch closes and Vx goes low. So you can sense the state of something using that limit switch. Okay. So if the switch is open, Vx is 5 volts. If the switch is closed, Vx is 0 volts. Now, some electromechanical systems, and they can get complex when you look at the complete schematic. I'll show you one. They implement control entirely using mechanical switches like limit switches and human activated switches and relays or solenoids versus using some kind of electronic controller like a microcontroller or like a digital circuit. One pretty complex example, and I'll show you the schematic, is a landing gear mechanism in an airplane. This is a retractable landing gear mechanism, right? So, and this is actually all done without semiconductors. Like, you know, you think about what you have to control here and what you have to work with, right? So you have to sense when the gear is down so you can give the pilot a green light, right? That lets the pilot know, hey, the gear's down, you can land, your gear isn't going to collapse, it's in the correct position. If you don't get a green light, you better go troubleshoot. There's a weight on wheels switch, which says, okay, if you're on the ground and you put the pilot controlled switch in the up position, don't retract the gear. So you have to know, is the plane on the ground or not? And that's typically done with a weight on wheels switch. You'll hear that in the military for aircraft also. So you'll see there are also throttle position switches. So throttle position switches, they warn the pilot if the throttle's pulled back to idle and the plane thinks the pilot wants to land and the gear's not down. So warn the pilot, the gear's not down. Don't land the plane like this. There's a motor arm position that's essentially an up position that tells the gear to stop running its motor up. And then the pilot actuates a gear selection switch, right? So here they are down here. This is a more rugged, what you'll see like a mil-spec or an industrial limit switch here. So that's a switch. Here's another one here mounted on the gear. You can see there's a plunger right there, and then as the gear changes position, you have this arm and this plate that make contact. Here's the landing gear up down pilot controlled switch. Okay, so those 9 switches, you have 9 switches in the system, control the motor gear the landing gear motor, whether the motor runs or not, and the direction, does the motor run forward or backward, right? So that's got to be controlled here. You need the indicator lights lit up when the gear is either up, down, or in transition in the middle. A warning horn if you shouldn't land because the gear is not fully down. And there's some other mechanisms and accessories in the plane that can be controlled, like a heater. You want the fan running when the plane's on the ground and there's not enough airflow. But I throw all this out there not to teach you about landing gear, but just to show you there are some complex electromechanical systems that use just switches in order to do this control. And here, in fact, is the schematic of such a system. And you know, it looks kind of complicated, and it sort of is. There's a lot of wiring going on here, but basically this is all controlling the gear motor. That's the primary controlled device here. Here's the gear relay, gear solenoid. We'll talk about those, right? And then you got to control those. And then there's a gear horn and indicator lights that have to be controlled, right? So all these devices have to be controlled by these 9 switches. And so you can see multiple pulls and multiple throws on these switches. Look at this one up here, the gear selector switch. That is a really complex looking switch there with lots of wires going to it. And so all of this does what I described on the previous slide. So these, the gear switches, the limit switches, the pilot actuated switches, they all make the control work with this wiring, and not a single semiconductor in here. So it's pretty interesting to look at this. Okay, so got to give some respect to the mechanical switch for getting this whole system to work. But I mentioned a relay here, so let's talk about relays. So relays are electromechanical devices, and basically the relay has a current through a coil. Like, you apply a current through a coil that creates a magnetic field, and that actually pulls apart switch contacts or pushes together switch contacts. And here's a schematic symbol for that. So here's the coil. You would energize that coil by applying a voltage across those 2 terminals. Current flows, creates a magnetic field, and in this case would probably pull that switch shut. And so you would connect your device with a power supply to these contacts here. And relays can be single pole, single throw, or multi-pole, multi-throw. Right? So you can get them in various configurations. Here's an example. This is a nice example of a relay. It looks like with the cover pulled off. You can look at these. You can search the web for these references to see these pictures if you want to zoom in and check them out more closely. But here's the coil. You can see the coil of wire, right, wrapped around. This looks like it's mounted on a circuit board. And here are the contacts. So those contacts right now look like they're in the open position. And if you energize this coil, the magnetic field is created. This arm at the top gets pulled down. That pushes this contact or this plunger out and closes those contacts. So that's how those work. You'll see relays with solder terminals, and some are meant to go into sockets, so you could solder wires onto these terminals on this relay on the left. You can have small printed circuit board mount relays. Here are a couple that are meant for that. Here's a surface mount version of the PCB mount right here. So they can get pretty tiny. Here's an automotive version that has a connector on it. And so that's meant for cars so that you can replace that pretty easily. A screw goes through here, mounts somewhere, and you have a connector on the bottom. Okay, so relay advantages are, well, you don't have to learn transistors, right? That's one thing. You don't have to learn about transistors. You can apply a voltage to the coil and just get a device to turn on and off. That's pretty easy to do. And some relays, beyond that, some relays can handle very high voltages and very high currents. So you can power high voltage and high current loads with relays. They also handle AC or DC loads because you're really just opening and closing a switch. And they generally have very low resistance when turned on. And there's zero leakage current when turned off. So these two contacts, when they're separated. There's going to be no current flowing between them for DC. I'm talking DC, not high frequency. Okay. Disadvantages of relays are they're fairly slow in control. So it's going to be the time that it takes to energize that coil and, push these two contacts together. So that takes some time. Okay, and they are generally large in size compared to a transistor. So if you have a really small circuit board, a really small device, maybe you want to consider a transistor. And they generally take larger control current, that's the current through the coil, compared to a transistor. So you might be able to use a milliamp to saturate a BJT to make current flow to a load, and that you might take a few milliamps or more to energize the coil to make these contacts close. You'll have an audible click. So if you have a device that has to turn on and off and it's in your bedroom and you don't want to hear the clicking of it on and off all night, well, that could be a problem. And so you'll probably hear that. Depends on the device, how big it is. And there's also a coil flyback voltage, right? In lab, you have that reverse bias diode in your motor driver circuit. Well, here's another coil. That coil generates a magnetic field. And when you try to stop that magnetic field, you get a big voltage, a large voltage created. Remember that voltage across an inductor is L didt. Didt is the slope of the current. If you try to shut off the current very fast, that's a very big slope. And so you get a rapidly collapsing magnetic field that creates a big voltage. And so you get this flyback voltage across the coil. And so it's good practice to use a normally reverse bias diode there to dissipate that stored energy, so you don't have that high voltage destroy whatever the coil's connected to. Okay, so relays are sometimes called solenoids when they're in this form factor. This looks like some kind of starter relay or some high current relay. And so you'll hear the word solenoid used in the context of controlling high DC currents to loads. So just think relay. You'd apply a control voltage, and that would close contacts, and then large amounts of current could flow. There are solid state relays, and they operate differently than mechanical relays, and they're typically optocoupler controlled transistors or silicon controlled rectifiers or triacs. So we're not going to talk about those, but you can go search the web for these and see lots of products out there that do this. Okay, so switches and relays, those are very mechanical, right? Which is fine. They have their place. Okay. Someone asks, in the chat, would a bounce be considered a relay disadvantage? Absolutely. So when we talk about switches in the Intro to Circuits class, switches and relay contacts are what I like to call scratchy devices, right? They're rough. Those contacts on a microscopic level are rough. So when they push together, they hit, they slide, and that causes on a very zoomed in level connects and disconnects often as transitions happen. And they might be milliseconds apart, but you can get what are called bounces, which means that the switch looks like it's opening and closing a few times, or the resistance is changing of those contacts mating as the switch closes or opens. That's called a bounce. And if that's connected to a digital circuit that's, say, counting edges, then you can get multiple counts registered when the switch bounces. Well, relays do that same thing. So if you were using this relay, maybe this relay is controlling a load, you're trying to count how many times the load is turning on and off by looking at the load power, the load side of this, the contact side. Well, then you could get bouncing. So you'd have to write, in software, there's some code you can do with a delay to mitigate switch bouncing as seen by the microcontroller. Or you can put a low pass filter and handle this in an analog way on the contact side. But that would be a disadvantage. You can get bouncing seen at relay contacts. Okay, so let's move into talking about the electrically controlled devices for controlling current. So you're using a MOSFET in lab to control a motor. So MOSFET is a metal oxide semiconductor field effect transistor. And so what you do with a MOSFET typically is you use the MOSFET as a voltage controlled high current switch. Okay, that's what we're doing in lab. We're not really working with super high currents. In fact, we're working with low currents, but this is letting you work with a MOSFET. So you're using a MOSFET as a voltage controlled switch. You can also use MOSFETs as amplifiers. When we talked about BJTs in a prior class, we talked about amplifiers. You can control the current into the collector with the current into the base, and you can make that vary relatively linearly. You can do the same thing with MOSFETs. We're going to concentrate in lab on using MOSFETs as voltage controlled switches. Okay, so you can use MOSFETs to control DC motors that may require considerable current. And you can use MOSFETs as the driver element for pulse width modulation, so that you can pulse the power to the current. You wouldn't want to do that with a relay. You wouldn't want a relay open and close at a kilohertz to try to control the pulse width modulated power to a motor. So MOSFETs are really good at this. Okay, so this is an N-channel MOSFET, an enhancement type, and we'll talk about these types. There's various types. This is the kind you have in lab. Here is the schematic symbol. And so you got to identify the terminals to this device, right? So normally a MOSFET's considered a 3-terminal device with gate, drain, and source. And some special MOSFETs have a body exposed, but that's what this body terminal designator is here. But oftentimes that's connected to another terminal. The voltages and currents we're typically concerned with are these two voltages, VGS, the gate to source voltage. That's what you're using in lab to control the drain current. Okay, so VGS controls ID. Now we're going to look at VDS because we're going to look at these characteristic plots that show the relationship between these three values, VGS, VDS, and ID. So we have to have all of these defined. Okay, so for motor control and for even amplifiers, you use the gate to source voltage VGS to control the drain current ID. Okay, so here's a diagram, kind of a cartoon of the construction of an N-channel MOSFET. Okay, so when VGS is 0, so this is the source terminal here, this is the gate terminal, and here's the drain. And so I've indicated here, this is VGS, the gate to source voltage, and the drain current would come in here and come out the source. Okay, so when VGS is 0, you have this depletion region. So you have these different regions, this heavily doped N region, you have a P substrate, and in between you have this region with negatively charged ions, right? So this is the depletion region here. And when VGS is 0, the depletion region acts as an insulator. So if you look, now you have an insulator between drain and source. So coming back to the schematic symbol, between drain and source, that's where you usually want the load current to flow. You have an insulator. So I would consider this MOSFET to be off when VGS is 0 volts. And that's for an enhancement type MOSFET. We'll talk about that. Okay, but when you increase VGS beyond a certain voltage, which is called a threshold voltage, a current can flow from drain to source. Conventional current, right? Positive charge flow can flow from drain to source. That means ID is greater than 0. And that's because of the electrons that are attracted to this oxide layer. So you apply a voltage to the gate, between gate and source, and you're attracting electrons, right? We normally talk positive charges, I'm saying electrons now, but you create this channel through which current can flow between drain and source. Okay. And the gate is insulated from the structure. So the gate current, DC gate current, is 0. We talked about in lab, there's a gate to source capacitance. Let's leave that aside for now because you get this little amount of charge accumulating there. But at steady state DC, the gate to source current, or the gate current, is 0 because you have this insulator in here. Okay, you have that oxide layer. Okay, and so these figures are from, you can go down and look at the Wikipedia page and learn a lot more about the structure and see different diagrams. But this is basically how they work. This is a good way to start off the conversation about, well, what are the relationships between VGS, VDS, and ID? And we're going to talk about that next. All right, so let's talk about an example MOSFET application. You want to control a 12-volt DC motor with a 5-volt microcontroller. Okay, so you can't connect the output pin of a 5-volt microcontroller and apply 12 volts directly to a motor. So here's your 12-volt power supply. Here's your motor. And if you connect the motor like this, just as it's shown, the motor will run. It'll never stop. Remember, grounds are connected. These are a common node here. Okay, and you want to use a MOSFET as an electronically controlled switch. So here's your MOSFET. You would insert the MOSFET here. This is called low side switching on the ground side of the motor. So you have your drain, your gate, and the source, and the drain to source right here. That's what's controlling the flow, the current into the drain when this MOSFET is, I like to say, on. So the current would flow from drain to source and down to ground when the MOSFET is on. Okay, and so the gate to source voltage controls ID, the drain current. And the drain current is the current through the motor. So you can use a microcontroller to control VGS. right? So you have this control voltage that's 0 volts or 5 volts, controls VGS, and now you have control of the current through the motor. So when VGS is 0, no drain current flows, the motor stopped. And when VGS is 5 volts, the motor would run here, given we've designed this right. Okay, so that's basically it, right? That's what you're doing in lab. That's all you needed to know to get started on your lab. But there are some important details that we should work through, and I'll show you to determine, for example, what VGS is required for a given amount of current. If I need 5 amps through this motor for a given MOSFET, what does VGS have to be? Does it have to be 5 volts? Does it have to be 10 volts? Can it be 0.2 volts, right? What voltage is required out of that control signal to make that motor run for a given current ID? And so that's what we're going to talk about. All right, and since you're mechanical engineers, probably if you get into robotics or just any kind of electromechanical control, solenoids that might take some high current, just motors that operate things, MOSFETs are a very useful tool in your toolbox. And they're built into many specific motor drivers. So let's talk about what are called characteristic curves for a MOSFET. So here is, and we'll talk about the differences. Here's an N-channel MOSFET enhancement. And so this is what you have in your lab kit that you're using. Okay, so the controlled current ID depends on, well, not just VGS, not just that gate to source voltage, but also VDS. Right, so here we're bringing VDS into it. So you're going to have, when you have current flowing, ID flowing into the drain and out of the source. Okay, so IS equals ID in this case. That's why we're just concerned with ID, not IS at this point with this configuration. Okay, so characteristic curves describe the drain current ID versus those two voltages, the drain to source voltage and VGS. Okay, so this is a cartoon, and I'll show you a real one. This is a cartoon of characteristic curves, nicely spread out so we can interpret them for a MOSFET. Okay, so you're controlling drain current. That's the vertical axis here. That's the current you want to control. And then you have this family of curves that relate drain current to the drain to source voltage, right? The drain to source voltage is the voltage across the MOSFET, but usually that's kind of your power supply voltage here, right? Drain to source here. And so those are two of the variables, and the third variable is shown as these families of curves. So here's VGS. So for VGS equals 7 volts, here's the curve. Right? For VGS go up to 8 volts, here's the curve. Go down to 5 volts, here's the curve. So there's a family of curves here. Okay, so in this case, 9 down to 4 volts. Okay, so the threshold voltage is the minimum gate to source voltage that is needed to create that conducting path between the source and the drain. So that's why down here, I show 4 volts right on the horizontal axis, because at 4 volts, you get 0 drain current. If you have less than 4 volts, you have no current flowing through this device. So that's the threshold voltage. And so you get over 4 volts, and then you've created a conducting path. But right at 4 volts and below, there's no drain current. ID equals 0. So for for VGS, gate to source voltage, less than V threshold, there's no current. The MOSFET's in cutoff. ID 0 amps. Okay, and when you increase the gate to source voltage above the threshold voltage, current flows. And the way that current flows is described by 2 regions of operation, either the linear region, also called the ohmic region, or the saturation region. Okay, so you see those here. I've put this dotted line to try to separate where the linear region is separate from the saturation region. And so in reality, the linear region is, well, where you have this upward slope that's almost linear. And the saturation region is really over here on the right, where you have these sort of almost flat lines. Okay, so there's kind of a, it's a little loose where one region begins and one ends. But nonetheless, in the linear region or the ohmic region, you have a nearly linear line, right? Nearly linear relationship between drain current and drain to source voltage. Okay, but there's a very steep, a very high slope for ID over VDS. Right? This is usually very steep here. Okay, and it's called the ohmic region because in this region, the MOSFET actually acts like a low resistance, like a resistor, like a low resistance resistor. And if you look at that slope, right, this is Ohm's law right here. V over I is R, right? V equals IR. So VDS divided by ID is what we define to be this RDS resistance, which describes that slope. It's a very small resistance because it's a steep slope. Okay. Notice these are reciprocals here. I over V is steep, V over I is shallow. So the resistance is low. So you could, in that region, essentially, we'll talk about this more, you could replace drain to source with a low valued resistor. That's what it acts like anyway. In the saturation region, the gate to source voltage, VGS, controls current independently almost of VDS. Okay, so right here you see that these lines are almost flat. They're not exactly flat, but they're almost flat. Okay. And current changes as you change VGS. Okay, so if you start at 5 volts, you get a certain current. Increase to 6 volts, you get increased current. 8 volts, increased current. And if you change the drain to source voltage within reason, since these are almost flat, the current is almost independent of VDS because that line isn't exactly flat. But there is little change in ID as you change VDS. So those are the characteristic curves. This describes the relationship between these three values, VGS, VDS, and ID. And so we're going to use this to control current into a device. We're going to do power control, not amplifiers, but this is what we're working with here. Okay. Okay, so let's talk about using the MOSFET in that linear ohmic region and the saturation region. So in the linear region, here's the MOSFET. Here's VGS, VDS, ID. That is essentially a switch that's controlled by VGS. Right? So when VGS is less than V threshold, you're at cutoff. The switch is open. That's when I say the MOSFET is off. So if you have VGS less than 4 volts in this example, the switch is off. It's an open switch. And when VGS is greater than V threshold, you're in the linear or ohmic region. That's a closed switch, right? So I have this closed switch here. And in reality, right, this isn't a straight up and down line. It has a finite slope. So in reality, there's a small resistance and there's a small voltage across this, quote, switch, right? That's that RDS value, right? The drain to source resistance there. Okay, so, but you can see how you have a switch that's either open or a really small resistor, just like a real switch has a really small resistance, probably less than this, but it acts just like a switch. In the saturation region, right? So I put this pink outline around here where these lines are about flat, right? They're about horizontal. So here's the MOSFET, and it's really a voltage controlled current source. So you're using VGS to control ID. So you can see ID controls VGS. So go back to circuits class. This is where, and I think I mentioned even in circuits class, if you want a voltage controlled current source, you want to see what that's like, then take my next class, because that's a MOSFET. And so here it is now. This is a this is a voltage controlled current source. It's a current source controlled by a voltage. It's some function of VGS. And so you can control a large amount of current with a voltage, and that's an amplifier, right? Okay, so there are two ways to visualize how to use a MOSFET, either as a switch in the linear region or as an amplifier in the saturation region, right? And these terms are different for BJTs, right? If you remember that, but I don't want to go down that path right now, but we can talk about that at office hours if you'd like to. Okay, so here's my cartoon. Let's look at some real curves. So let's look at the curves and data sheet for the MOSFET you're using in lab, this IRFZ44N. It's an N-channel enhancement MOSFET. We'll talk about that. So this is the part right here. And so what you really have to do is you have to look at the data sheet for a particular MOSFET specific to its part number to look at the characteristics. And then you can dig into those data sheets and find the characteristic curves. And so these characteristic curves will show you the expected performance. So, here's this is not the cartoon, this is the real thing here. But we have the same axes here. We have the drain current, here called drain to source current, versus drain to source voltage. And then for various VGS values here. Right? And VGS is called out here. So the bottom line here, that's 4.5 volts. That's called out. Here's the bottom, here's the top. The top line here, that's 15 volts. And you kind of have to mentally fill in or handwrite in, if you want to not make mistakes, all the values of these voltages in here. But this is the family of curves for these different VGS values. Okay, so also notice these are log scales. So I have a log scale here for drain current. I have a log scale here for VDS. Notice these curves aren't perfect. I mean, look at this. This isn't exactly flat, and it has some like funny downturns here. So, right, this is what you get when you're dealing with real devices and not cartoon characteristics. So the tables in the data sheet show parameters like the threshold voltage and the on resistance, RDS. So you look in this data sheet, if you break out of this, here's RDS, the on resistance, the drain to source resistance. So 17.5 milliohms. So it's a really small resistance. That's good. That's what you want out of a switch, right? You want a really small resistance. And for these particular values, right? This is VGS equal to 10 volts and ID equals 25 milliamps, right? So if you go down to the curve here and you calculated the slope on this log scale, if they take two different current values, two different voltage values, take the difference, calculate V over I, delta V over delta I. And so you'd see in here that at 10 volts, 25 amps, you'd have VGS, you'd have 17.5 milliohms. And then you have the gate to source threshold voltage. So for this particular transistor, the one you're using in lab, this MOSFET, you would expect to, if you really want to be sure that you're hitting the threshold voltage, you have to have over 4 volts to make sure that you're above that cutoff. Now, under certain conditions, it looks like the minimum value for the threshold voltage is 2 volts. But I had picked this transistor in lab because I knew you were using a 5 volt Arduino. You're using a 5-volt microcontroller. So I knew you were going to have more than 5 volts, 5 volts or higher, a little bit higher control voltage. So this transistor works just fine. This MOSFET works just fine for your application. Right? Okay, so that's what a real set of characteristic curves looks like for the transistor, the MOSFET you're using in lab, and you've got some data sheet values you can look at here too. We will dig into this MOSFET topic a little more next time, again, to get you familiar with what you're doing in lab and how that's working. But it looks like I've hit the wall on time. So in closing, always keep an eye on Canvas for the due times and the due dates. Those are all posted. I think your next homework isn't due until next week, but check me on that. The exam solutions will be posted once I confirm I have all the exams, and and take a look at that. I will start office hours in just a few seconds. So if you'd like to chat about anything, class questions, anything else, or just listen in, go ahead and stop by. If you don't join, I'll see you next time. Have a great night.